Take any matrix, any size, any numbers, row reduce it, and something remarkable happens. The number of directions it can reach plus the number of directions it kills always adds up to the same thing. The number of columns. Always. No exceptions. This is the Rank-Nullity Theorem, and it works like a budget. Every column gets spent with nothing left over. Let's look at a few examples. A 2x3 matrix has 3 columns, its rank is 2, and its nullity is 1. 2 plus 1 equals 3. Check. A 3x4 matrix has 4 columns, rank 3 plus nullity 1 equals 4. Check. A 4x5 matrix has 5 columns, rank 3 plus nullity 2 equals 5. Check. Even a 2x2 matrix. Rank 2 plus nullity 0 equals 2. Check. In every case, the central equation holds. Rank of A plus nullity of A equals n. Let's see why this budget can never be broken. Consider this 3x4 matrix A. Row 1 is 1, 2, 3, 1. Row 2 is 1, 1, 2, 1. Row 3 is 1, 2, 3, 1. This matrix has 4 columns, so our budget from the Rank-Nullity Theorem is 4. Before computing anything, let's look at the columns carefully. Column 3 equals column 1 plus column 2. Check each entry. 1 plus 2 is 3. 1 plus 1 is 2. 1 plus 2 is 3. It checks out perfectly. Now look at column 4. It is identical to column 1. So at least 2 columns are redundant, meaning they are built entirely from the others. This tells us the matrix cannot possibly have 4 independent columns. Row reduction will tell us exactly how many independent columns it does have. Let's row reduce. We subtract row 1 from row 2. Entry by entry, 1 minus 1 is 0, 1 minus 2 is negative 1, 2 minus 3 is negative 1, and 1 minus 1 is 0. So row 2 becomes 0, negative 1, negative 1, 0. Now subtract row 1 from row 3. Row 3 was identical to row 1, so every entry cancels and it becomes all zeros. The echelon form is row 1 is 1, 2, 3, 1. Row 2 is 0, negative 1, negative 1, 0. Row 3 is all zeros. Now we identify the pivots. The first pivot is in row 1, column 1. The second pivot is in row 2, column 2. There are no more pivots. Columns 1 and 2 are pivot columns. Columns 3 and 4 are free columns. The rank, defined as the number of pivot positions, equals 2. Here's the key theorem. The pivot columns of the original matrix, not the echelon form a basis for the column space. A basis is a linearly independent set of vectors that spans the space. Our pivot columns are columns 1 and 2 of A, the vectors 1, 1, 1, and 2, 1, 2. Let's verify these are linearly independent. If we set up C1 times 1, 1, 1 plus C2 times 2, 1, 2 equals 0, we get the system C1 plus 2, C2 equals 0, and C1 plus C2 equals 0. Subtracting gives C2 equals 0, which forces C1 to equal 0 as well. So they are indeed independent. These two vectors span a plane through the origin in R3. That plane is the column space, and its dimension equals 2, matching the rank. Important distinction: rank is a property of the matrix. Dimension is a property of the space. They agree numerically for the column space, but they are different concepts. One common mistake is using pivot columns from the echelon form instead. The echelon columns 1, 0, 0, and 2, negative 1, 0 are different vectors lying in a different plane. Row operations preserve column dependencies, but they change the column space itself. Always use the original matrix. We found what the matrix reaches. It's column space. Now let's find what it kills. It's null space. All vectors x where ax equals the 0 vector. From the echelon form, the equations are x1 plus 2, x2 plus 3, x3 plus x4 equals 0, and negative x2 minus x3 equals 0. The pivot variables are x1 and x2, since those columns contain pivots. The free variables are x3 and x4. A special solution sets one free variable to 1 and the rest to 0, then solves for the pivot variables using back-substitution. First case, set x3 equals 1 and x4 equals 0. Equation 2 gives negative x2 minus 1 equals 0, so x2 equals negative 1. Equation 1 becomes x1 plus 2 times negative 1 plus 3 times 1 plus 0 equals 0. That simplifies to x1 minus 2 plus 3 equals 0, which is x1 plus 1 equals 0, so x1 equals negative 1. Special solution S1 is the vector negative 1, 1, 0. Second case, set x3 equals 0 and x4 equals 1. Equation 2 gives negative x2 equals 0, so x2 equals 0. Equation 1 becomes x1 plus 0 plus 0 plus 1 equals 0, so x1 equals negative 1. Special solution S2 is the vector negative 1, 0, 0, 1. These two vectors form a basis for the null space. The nullity, the dimension of the null space, equals 2, and that matches n minus r, 4 minus 2. A common misconception is that only pivot columns can serve as a column space basis. That is not true. Any two independent vectors in the column space will work. For example, columns 1 and 3, the vectors 1, 1, 1, and 3, 2, 3 are independent and span the same plane as the pivot columns. Even the pair 2, 2, 2, and 7, 5, 7 works. Since both vectors lie in the column space and are linearly independent. So we have three different bases, but the dimension is always 2. The same idea holds for the null space. Other bases exist beyond the special solutions, but every basis has exactly n minus r vectors. The dimension is the invariant, not the particular choice of basis vectors. The basis can change, but the dimension cannot. Here's why the formula must hold. After row reduction, every column is either a pivot column or a free column. There is no third option. Think of the total number of columns as a budget that must be completely allocated. The R pivot columns fix the dimension of the column space. The n minus r free columns each produce one independent special solution, fixing the dimension of the null space. Now add them together, r plus n minus r equals n. In our example, 2 plus 2 equals 4. The column count is the budget, and it is always exactly spent. This is the Rank-Nullity Theorem. Rank plus nullity equals the number of columns. This is the Rank-Nullity Theorem, a cornerstone of linear algebra. It states that the rank of A plus the nullity of A equals n, the number of columns. It constrains every linear transformation from Rn. Directions either map to new places in the column space, or they collapse to 0 in the null space. The total budget is always n. For our matrix, rank 2 plus nullity, 2 equals 4 columns. The idea extends even further. Every matrix has 4 fundamental subspaces. In Rm, the codomain, we find the column space and the left null space. In Rn, the domain, we find the row space and the null space. The rank R appears in both the column space and the row space, as each has dimension R. Meanwhile, m minus r and n minus r fill the remaining dimensions in Rm and Rn respectively. This gives us the complete picture of how a matrix organizes space. Rank tells you what the matrix can reach. Nullity tells you what the matrix destroys. And the number of columns is the budget that's always perfectly spent. Rank points to the column space, the set of all outputs A can produce. Nullity points to the null space, the set of all inputs A sends to 0. And n, the number of columns, is the total budget, always divided completely between these two. For any m by n matrix A, rank of A plus nullity of A equals n. Every column becomes either a pivot, building the column space, or a free variable, building the null space. Two groups, one equation, no exceptions. In our example, the budget bar confirms it. 2 pivot columns plus 2 free columns equals 4 total columns. Check.